Hello and welcome to the third video of the Labgrid tutorial series. In the last video, we learned what Labgrid drivers and Labgrid strategies are. We used the barebox strategy to transition our board into various states, for example, the barebox shell state or the Linux shell state. In this video, I will show you how to automate recurring workflows and create automated tests using Labgrid strategies. Here's Labgrid's documentation. Let's look at the usage chapter in the library section. This part of the documentation explains us how to use Labgrid as a library, so we can create scripts that automate certain steps. On the left-hand side, I have just activated our Labgrid virtual env. If you want to see how this was set up, look at the corresponding documentation chapter in the Labgrid documentation or watch the first video of this tutorial series. We will start by installing IPython in the virtual env. IPython is an interactive Python command shell with syntax highlighting, tab completion, and more. It is very useful for trying things out, getting a feeling how a library works, but it also can help us debugging. Now we can start IPython and import Labgrid. We will start by instantiating the Labgrid step reporter. Certain operations in Labgrid are recorded as steps, for example transitioning into a strategy state. The step reporter prints these steps to standard out. We do not strictly need that, but it helps us understand what happens with our board. This is the same output we see when we transition into a state using the command line interface Labgrid client with -v verbosity. We continue by creating an environment object from the environment configuration we created in the last video. Then we create the target object. Remember, we described our board in the environment configuration under the targets key in the last video. The next step is the instantiation of the strategy. Similar to the last video, we will stick to the barebox strategy for now. In the next video, we will create a custom strategy. We already learned that a strategy is a special driver, so we can use the get_driver method on the target object. To keep things generic, we can use the string strategy here. This works because each strategy inherits from the base strategy class here, and we can only have one strategy per target, so Labgrid knows what we mean here. On the strategy object, we call the transition method to switch into a state, just like we did on the last video with Labgrid client's -s or ---- state argument. We will try the state barebox first. Our board has now reached the barebox shell. We can now interact with the barebox driver using the barebox attribute. This works because the attribute barebox is mapped to the barebox driver in the binding map of the barebox strategy. We learned that in the last video. The driver is already instantiated. That's what the strategy took care of. We can now, for example, run the barebox shell command devinfo. It shows us a summary of the devices the barebox bootloader knows about on this board. The run method returns the output as well as the exit code of this command. There is also another variant of this method called run_check, which will raise an exception if the exit code of the command is non-zero. We can use the false command to do nothing unsuccessfully. We could now transition to another state, for example, shell. Here, the barebox driver looks for the Linux kernel version string, handing over to the shell driver. That looks for a prompt or a login. Now we are logged in. Similar to barebox, we can run commands here like ls/. Let's do another transition to the off state. And from here, we can reach barebox again. So, using Labgrid as a library, you can automate workflows, run commands, basically everything you have to do over and over again. Just put the commands we ran here in the IPython shell in a short script and run it. If you hunt a bug, you could even run a full automated git bisect with this method. Next, I'd like to show you how to write and run automated tests using the Labgrid PiTest plugin. First, we create a directory. Let's call it test suite and switch into it, here and here. In this directory, we create another directory called tests. This follows the basic concept of how PiTest expects its tests being organized. In the Labgrid documentation, scrolling down to PiTest plugin, we see how it is meant to be used. On the left-hand side, I show you the output of PiTest --help. See, there is a section about the Labgrid PiTest plugin because we are running PiTest in the Labgrid virtual environment we set up in the first video. We need to specify some options to run PiTest with the Labgrid PiTest plugin. Additionally, Labgrid prepared a set of fixtures for us to use. If you have not used PiTest before and you don't know about fixtures, let's look that up quickly. This is how a fixture looks like, a Python function with a fixture decorator. On the bottom of the green area, you see how it is used. Simply add the name of the fixture function as an argument in the test function. PiTest makes sure to run the function before. The return value of the fixture function is then stored as the argument. By default, PiTest looks for a file called conf_test_py and executes that. We store our custom fixture in that file. Let's create a fixture called barebox. A fixture can use other fixtures. Labgrid offers the strategy fixture we will use here. When this fixture is used, we transition into the state barebox. And our fixture then returns the barebox driver. You will see in a second why that makes our tests much cleaner, much more readable, and saves us from code duplication. Now we will create a test file with an actual test case. In this example test, I'd like to test whether the bootloader on my board detects the eMMC or not. We use the fixture barebox we just created. So, when this test function is called, the board is already in the state barebox and we can access the barebox driver using the barebox argument. The run_check method makes sure an exception is raised if the command fails. That would lead to a failed test, just as we would expect. This barebox command detects all devices that are not probed yet. If the eMMC is not probed correctly, we should have a corresponding file in the dev file system called /dev/mmc0. The ls command will fail if the path does not exist, which would again lead to an exception being raised. That's it for the test function. Back to PiTest's help text here. Let's create the correct PiTest call. We need to tell the Labgrid PiTest plugin where our environment config is located with --lg--env. With the --lg--log option, you get the serial console written to a log file, completely unaltered. I'll show you that in a second. Another nice thing is --lg--colored-steps. A few minutes ago, I told you about Labgrid Step Reporter. This option makes the output of the step report more colorful. That helps us to distinguish the various types of steps. Finally, add two -v switches which activate the step reporting feature. Now we can run the PiTest command. While that runs, we can follow the log file it writes. The file is called console_target_name, so in our case console_main. That's why we use tail -f console_main. The board reaches the barebox state and executes our commands successfully. So, as you can see, it is very easy to write tests using Labgrid. Whenever you have a more complex setup, the strategies Labgrid ships will not be sufficient for your use case anymore. Next time we will see how you can write custom strategies, allowing you to use the drivers you need for your setup. We will also explore how you can automatically test the images your continuous integration system like Jenkins builds. That's it for this video. Thanks for watching and see you soon.